Woohoo! Welcome back to part 2 of 5.2, and we're going to focus now on some properties of logarithms. As I've mentioned here, there are more in the book that we won't use, but I am happy to go over any of them. If you'd like to do a deep dive on logarithms, that's awesome. But for this particular class, we're picking and choosing just the interesting parts of logarithms that's going to help us with what we really want to do in chapter 6, and that's talk about saving up money, investing money, looking at things like sinking funds and payments and all that cool financial stuff. So this section is going to be a very light review. So here we go. Here are the properties that we are interested in. The first is that logs and exponential functions are inverses. They undo each other. So in other words, if you take an exponential function and then you apply a logarithm, it undoes it, and vice versa. So let's take a look. So what does this mean in the real world? Well, up here I said log base a of a to the x equals x. And I'm going to write that bigger because I realize this is translating pretty small on the screen. I'm not sure if that's helpful. I got my squirrel friend here to support us. Yay, you're doing great. So if the base matches the base in the exponential part, then effectively all of this cancels out and you're just left with the exponent there. Now it has to be exactly this form. So if parentheses are involved, be very, very careful. However, if we've got something like log base 3 of 3 to the 4th, how many 3's multiplied together are in 3 multiplied together 4 times? Well, 4. If we're counting 3's and this is 3 to the 4, then we got 4 of those 3's multiplied together. Now, this one's a little more tricksy. This one was, you could see the 3's match. Here, when you get common log, remember, write it out with the base as 10, and then think to yourself, I bet I could rewrite 1,000 in terms of tens. So this is log base 10 of 1,000, which is 10 cubed. And then if you've got two matching numbers there in the middle, if this base matches that base, then the logarithm and the exponential part undo each other. I feel like I want to put a box around these. Makes it seem more fancy and formal. There we go. And I'm going to go back and underline the fact that that 3 and that 3 match as well. Okay. So now, oh no, dun dun dun. Part C is really hard, except it's totally not. First thing I'm going to do is not panic. Second thing is I see log, so I know that's common log base 10. And then I'm going to think to myself, oof, this can't be that hard. I could use my calculator, which is sitting right over there. But rather than do that, let me think to myself, how do you pronounce this number? This number is 1/100th, right? So this is log base 10 of 1 over 100, which is log base 10 of 1 over 10 squared, right? 100 is 10 squared. Sorry, let me move this over. And if I've got an exponent in the denominator, what I really have, log base 10 of 10 to the negative 2, right? 1 over 10 squared is 10 to the negative 2. And if you don't know that, you want to stop right now. Don't pass go, don't collect $200. Stop right now and go review exponents, or talk to me or talk to a tutor. Because if you don't understand negative exponents, there's going to be a lot of stuff coming up that's not going to make any sense. So you want to stop here, put the time in, give yourself a good, whatever it takes, an hour deep dive maybe to remember how to do that. Talk to me, talk to a tutor, make sure you sort it all out, then come back here Because the great thing about videos is you pause them and they're just paused forever. I'll just stop talking forever. Yeah, like that's going to happen. Okay, so here we've got the 10 and the 10. They match. Log base 10 of 10 to the negative 2. And at which point you say, wait a minute, didn't you say we can't have any negatives? And the answer is, well, we can't have negatives in certain places. The a, the base itself, has to be positive and not 1. And this number has to be positive and not negative. The exponent can totally be negative. So the answer can be negative. We just can't have this couldn't be negative 0.01. But the exponent totally could be negative. Woohoo! Okay, so that's part 1. Now part 2, and I know it's going to look, a lot of people when they see this, a to the log base a of x equals x. Well, now that you know that, you can use it. You can use it for good or for evil. Honestly, if you've got someone who is bugging you, you can say, hey, yeah, let's do this work. And that will scare off most people on the planet. Most people will just run and hide, possibly crying at the same time. So, this can be used to your benefit if you just want to be left alone. But on the other hand, a lot of people look at this and go, this is so much. So let's talk through what's actually happening. What's actually happening is I have a log, a regular old log base a of x. And I've put that in, weirdly enough, to the exponent as an exponent of a. So this is me taking the exponential piece and the logarithm piece together. And when they're put together, they undo each other. So if I raise a to the power of log base a of x, if these two things match, much like when these two things match, if these two things match, the x pops out, which is really useful. So what does that mean? Well, if I have e to the natural log of 4, don't panic. I know a lot of people at that point, they're like, ugh. Deep breaths. Keep your support squirrels around. E to the log base e of 4. And then we go, wait a minute. This e and the log base e, they match. And so you get 4. Yay! Okay, what about 10 raised to the power of log 5? Well, remember, if there's no base specified, it's base 10. Much like if you have natural log, it's base e. This is base 10. And is there a color I haven't used yet? Yeah, there's orange. Ooh. 10 raised to the power log base 10 of 5. These two undo each other, and our answer is 5. So now you're looking at all of this going, I don't remember it all from Math 60 when I took it, and I'm going to say, I know, most people don't remember it. We don't use it a lot. The people who use it all the time, and the rest of us generally don't use it that often. The good news is the way we're going to use these logarithms is going to be really consistent. So what I'm doing now is I'm trying to give you the tools so you've got some flexibility. But once we get into chapter 6, I promise you we'll do the same thing over and over and over, and you'll be like, oh, this is what we're going to do with it. So have faith. Have courage. And I'm sure I say this in millions of videos, but you know that the word courage comes from the French word, I believe, I hope I'm not making it up, it comes from the French word for heart, not for strength. It's cour. Courage means to have heart, not strength. Just keep that in mind. Okay, so I wrote a sentence up there that makes a lot of people laugh, I think. Logs are an easy way to work with exponents. At which point a lot of students would say, ha ha ha, no, they're not. And the answer is, I know. But I'm going to show you a really cool thing that happens. So Now remember, I did tell you to be wary of parentheses. So let's talk through this. Log base 4 of 16 to the x. Now, if the parentheses are around the 16 to the x, that's good. If the parentheses are anywhere else, run away. But if the parentheses, well, don't run away, but maybe talk to me, about how we're going to work through it. But if the parentheses are around the 16 to the x, we're good. You're golden. It does not change the order of operations. You can go, pardon me, squirrel, I need some space. I'm going to drop the parentheses. And then a magical thing is going to happen. If you have a logarithm of a number with an exponent, because basically what you're counting is you're saying, your logarithms say, what is the exponent, basically. So because of this, that exponent, I'm going to move you again, just right over there. You're right there. I know you're there. You don't have to be on camera. And what's going to happen is that this x that's up here is going to come down in front. So the x that was up here comes down in front right there. Sorry, you can't see the whole thing. There we go. So why is that helpful? Well, exponents are really hard to work with. Just take my word for it. In fact, in this case, there's kind of no other way to do this. But if we use the fact that when we've got the log of a number with an exponent, then that exponent comes out in front and then it's multiplied. And multiplication we can deal with. Because then I say, okay, well, I've got log base 4 of 16. What is log base 4 of 16? Well, let's think. Oh, part B is so much easier than this one. Log base 4. And what is 16? 16 is just 4 squared. So 16 is just 4 squared. And then this part right here, log base 4 of 4 squared, this whole thing ends up being just 2. What in the heck am I talking about here? This whole piece right there becomes just the 2. Why is that? Well, because the logarithm and the exponent are inverses, so they undo each other. Since the base matches the base, we just end up with the 2 left over. And then there's the x that was already just there. It was out in front. So we've got it, and it's just like that. Now, could we have done this without getting the x out of the way? No. So it's really convenient that the x just jumped out of the way. We could do this, simplify what's going on here, and then we end up with 2x, which hopefully I can convince you that the expression 2x, way easier to deal with than log base 4 of 16 to the x, right? Yeah. Okay, I'm not sure what I was thinking, but part B is way easier. What is log base a of a to the x? Well, if we use the previous section, these are inverses, so we just pop out the x. But what's another way to look at it? Well, we can let the x go down in front, and we get x times the quantity log base a of a. How many a's are in a? 1. Now, some of you are saying, wow, you took 4 steps to write out something we already knew. And the answer is, the cool thing about mathematics, one of the things that I think is the best thing about mathematics, is that no matter which way you go, if you go this way or you go that way, whichever way you go, you end up with the same result. So even though I did it fancy style, I still get that you end up with X. So, okay, one more piece of information. Now, some people love change of base. Some people adore change of base. I don't. And I don't know why. And the book loves it. So in this section and in chapter 6, if you read the book, and you're welcome to read the book is actually correct. But if you read the book is going to go really hard on the change of base. They love the change of base. So I'm going to go over it. But what's going to be weird is you're going to see me go over the change of base property, which I'm about to show you, which is easy peasy. It's not a big deal. But then I'm never going to use it again. Or maybe I use it once. And the reason for that is I don't think it's useful for the work we're doing. Is it useful overall? Absolutely. So what does it say? It says that if I have log base b of x, so any base, then I can calculate that using either common log or natural log. And in fact, any log you could use if you have a favorite log. I mean, I don't know. I guess as a mathematician, I should have a favorite log. I don't play favorites. They're all like children to me. I can't choose just one. But you can use any log you want. Why is this useful? Well, if you've got one of these calculators and you find yourself using log base 3 or log base 12 or log base 17, if you look at this calculator, there is no log base 3 or 4 or whatever I said, 17. There's common log and natural log. So this is the formula that allows you to do it. If you've got a fancy calculator, you don't need this because the fancy calculator actually has... Remember, if I show you here, this particular one, if I click it once, I get natural log. If I click it twice, I get common log. And if I click it 3 times, I get this thing that says log base. And I could make it log base 17 if I felt like it. That is an option. It's that powerful. So if you have a calculator like this, you never have to do the change of base unless the problem gets really complicated. So let's pretend we just have this calculator and let's go ahead and work this out. I want us to calculate log base 3 of 7. So basically what the change of base form says is you can set this up, and this is really cool. It's just a ratio. You pick log or natural log. I'm going to do common log, and the argument goes on top and the base goes on the bottom because it's kind of how they're already situated. The 7 is a little bit higher up, so that goes up on top, and the 3 goes down below. You can also use natural log, or you can use any log you want, but those are the 2 logs. Oh my goodness, what was I thinking? Oh, look over there. Don't look here. What? There's nothing here. I think there's like a pterodactyl sneaking out of your closet. You should check. Go check your closet. Make sure there's no pterodactyl. Because pterodactyls in the closet, they'll just try on all your clothes and get them all wrinkly. Yeah, pterodactyls, well known for, breaking white out and wearing all your clothes and getting them all wrinkly. And you're just that's no good. Okay, here we go. I'm sorry. I must have been mistaken. I don't think there is a pterodactyl in your closet, but you should double check anyway and then come back. Okay, there we go. Oh, thank goodness I didn't make any mistakes. So, actually I did. I made a big mistake and yet I fixed it and here we are and life goes on. It's actually a great opportunity to say, hey, if you make mistakes, you can be silly and tell people there's a pterodactyl in their closet, or you can just say, I made a mistake, let me fix that. Okay, so here's the common log. And I know, I can sense that you guys are all very excited. I do want to go over this, because I want to show you, because there is a sneaky thing that will happen. So here I go, log of 7. Now notice how the logarithm on this calculator has a parenthesis. If I go right into divided by log of 3, hopefully you see what's happening. This swallowed the logarithm, right? The logarithm fell inside. Logarithms can fall inside each other really easily. So when I do log of 7, make sure you close the parenthesis. Do you see that? I closed it. And then divided by log of 3. And I get that beautiful number. And it doesn't tell me how to round it, so I'm just going to leave it as the raw number. ... Let me try it. Now I know you're all thinking, but you can't possibly get the same answer with natural log. Well, let's check. Natural log of 7. Again, remember to close the parentheses. Divided by natural log of 3. Those parentheses. And I get 1.771243, some other numbers. Ta-da! Same number. And just because I know some of you are going to be like, wait, that was way too easy. I don't think that's true. Then I'm going to go ahead and I'm going to use this log key. And remember, this log key, if I click it once, I get natural log. Twice, I get log. 3 times log base. And I believe I plug in the 3 here. Of 7. I really hope I'm doing it correctly. Ugh! Do I do a comma? No. Okay. So I thought just on the fly I could figure out how to do this. Yeah. I'm going to have to look it up. So I apologize. I do not know how to use... Yeah. Okay. I'm going to stop wasting your time. There is a way to do it with this. I just don't know how. So I'm rusty. As you can tell, I don't calculate a lot of logs. But if you're curious, I will show you how to do that. I'll have to figure it out first, but I'm sure it's something I could Google. Okay, are you guys ready for... I know it's very exciting. The last page! I'm certainly ready for the last page. I hope you're ready and excited for the last page. Dun, dun, dun! I'm going to bring our squirrel friend back as for support, because this problem is going to be somewhat confusing. So there are 2 perspectives on assigning homework. One perspective is you only ever give people the easy ones that make sense because you don't want to give them the confusing ones because that's just mean. The other perspective is you give them the confusing ones as practice to build strength and resiliency, right? When you come up against a homework problem that's ridiculous or stupid or tricky or mean, you hopefully, as you gain more practice with them, you realize, wait a minute, you can totally handle this. And if you can't handle it, you ask for help, and then you can handle it with help. So everything is doable here. And so my perspective is I go ahead and I assign these weird problems from the homework, and I show you how to do them. So this is number 72 in the actual book, which is not the number that you get in your homework, but it is number 72 out of the book. And I say, I'm going over this problem here because the book uses an unusual form in the homework for this section. It's really unusual. So this thing that we're going to do, this is a preview of what comes up in chapter 6, but this is not the way we do it in chapter 6. This is just weird. This is the only place I've ever seen this happen. And maybe once when I was an undergraduate. But the teacher was terrible, so I can't, no. So hopefully it doesn't mean that I am being a terrible teacher. So this has to do with doubling time. And the really cool thing about interest is that for a given interest rate, and I know this is bonkers, 7.2%. I don't know when we're going to see that kind of interest in the future. Maybe you're a bank and you've given someone a credit card and they're paying you the 7.2%. But basically, if you have a given interest rate and a given type of compounding, so remember, compounding is how often you calculate the interest, and here it's monthly. So every month we're going to calculate the interest. The question is, how long will it take to double your money? And the really cool thing is, it doesn't matter how much money you start with. So if you start with $5, this will tell you how long it'll take to get to $10. If you start with $2, this will tell you how long to get to $4. If you start at 1 million, it'll tell you how long to get to 2 million. So the doubling time is a property of the interest rate, and it has nothing to do with how much you start with, which is pretty cool. I think it's really cool. It's money and it's fun. Okay, so, woohoo. We have this formula. So far, it shouldn't look that weird to you. I've got 2 equals quantity 1 plus r over 100 n to the nt. And we're told that r is the interest rate. This is what's weird. R is the interest rate in interest rate form, not decimal form. So r is 7.2. This is really bizarre. This is really bizarre. I've been teaching out of this book for probably a couple hundred years at this point, and I still don't understand why they did this. Why confuse everyone? Okay. See where the 100 is down there? It's going to be what takes this and turns it into a decimal. But I don't know why they do that. Why do that? I don't know. Okay. It could be maybe all of you will graduate, you'll go take your finance classes, you'll come back and say, oh, well, even though mathematicians would never do it this way, everyone outside mathematics does it this way, which is possible because, mathematicians, I don't get out that often. Okay, R is 7.2, interest rate. N is the number of times the interest is compounded per year. Now, how do we know what that is? N is the number of times the interest is compounded per year. We'll do it Dora the Explorer style. I'll say, do you see Swiper? Or do you see how many times it's compounded per year? I do. Monthly. You did it! Yay! So if it's compounded monthly, it's 12. Now, I know a lot of people, you're all worried. You're like, what if it's something else? And the answer is, we're going to deal with that in chapter 6. We really will do a deep dive, and we'll talk about this. I have a whole chart. If it's every year, then it's 1. And if it's semi-annually, then it's 2, etc., etc. We work the whole thing out. So, breathe lots. Chapter 5 is all about preparing for chapter 6. Okay, I've got an R, I've got an N, I've got an N, and I've got a T. And you'll notice I've got an R and an N, but no T. And the answer is, use this formula to find the doubling time. So T is the doubling time. And that's the thing we don't know. That's the unknown variable. Okay, let's plug this in. I got a 2. I got a 1 plus 7.2 all over 100 times 12 to the... Can I save this to the 12t? Hopefully that looks almost like writing. Okay, so far so good. So a couple things we can do. You don't have to, but you can simplify this inside. And here's the thing, remember, never round in the middle of a problem. But if you can work something out exactly, then that's totally fine. And if you'll notice, if I do 7.2 divided by, notice I'm going to use parentheses because there are 2 things in the denominator, 100 times 12. I could have also written in 1200 if I wanted. And so this value is going to be 0.006. So I can simplify. If it works out exactly, do that. If it doesn't work out exactly, then you're stuck. You have to leave this in this form. If this does work out exactly, I can go ahead and add the 1. So it becomes 1.006 to the 12t. And now we have to remember, oh my goodness, how do we get a variable out of the exponent? And the answer is, and I should have a superhero logarithm, and I don't have a superhero logarithm puppet made up. Oh no. But basically, what do? We bring in log. Yay, yay. And I think the last time we did it, I used common log, so I'll use natural log. Can you use common log? Yes. Can you use log base 17? Yes. Any logarithm you want. I'll use natural log. Also, the book seems to think you have to use certain logs. The book is well-meaning, I think. I don't think it's actually evil. It just kind of seems that way sometimes. But you know, sometimes people in books try really hard but they end up just seeming kind of evil and you don't understand them, and that's me in the book. Okay, natural log of 2 equals natural log of 1.006 to the 12t. If I haven't said it in a million videos already, remember, my perspective is you always write down exactly what you ended with to begin with. Don't try to do any math when you switch pages. Okay, so I've got, oops, let me push that all. Oh, you don't want to be left out. There you go. Okay, just sit there. You'll be fine. Okay, remember what happens when you take a logarithm, whatever's in the exponent comes down. So I get natural log of 2 equals, and then this guy comes down in front, so I get 12t times natural log of 1.006. Now, your eyeballs are going to see that there are a lot of letters running around, right? The letters. Remember that natural log is, it's not a variable. This is actually a calculation that we have to do. The variable is right there. So what we're going to want to do is move everybody that's not that t variable by dividing. I'm going to divide out the 12 and the natural log of 1.006. And I'll do that on both sides. So then I get t is the only thing left, and then I get natural log of 2 all over 12 times natural log of 1.006. Okay, then we'll bring in our calculator. Yay! Natural log of 2. Notice the parenthesis open, so I close the parenthesis. And now since that's my numerator, I'm going to go ahead and evaluate it. Okay, that's my full natural log. Now to go in the denominator, I'm going to divide. Right? I divide. And then I'm going to start open a parenthesis. 12 times natural log of 1.006. Now I have to close the natural log and I have to close the other parentheses. I know that was a lot. So let me take a moment. I know everyone's waiting and they're like, what's the answer? So I'm going to do my natural log key and then 2, and then I close the parenthesis, and then I do equals, or if you have an enter, depending on, and then I'm going to do divided by, right, to get to the denominator. Then I'm going to use parentheses to keep this all together. If you don't do that, it will only divide the first thing. You have to put parentheses around it. I'm going to say 12 times natural log of 1.006. And here's the thing. So this natural log goes with, every time you open a natural log, you have to close it. This natural log right there goes with this. Open natural log, close it. And then this parenthesis goes with that parenthesis. And in the actual problem, here's my blue piece right there. And here's my pink piece right there. Okay, you ready to hit enter? This is exciting. How long does it take to double your money? What does that mean? Well, this is years. You wouldn't know that otherwise. I'm not sure it's actually specified in this problem, but once you get into chapter 6, you get used to it. So now we're going to do something fancy. Doubling time. So it doesn't say what we're supposed to round to. So if it says round to the month. Oops, sorry. I don't want to do month first. I'm going to say if it says round to the years, then what would we round to? 9.65. I would say it's going to take 10 years. And in fact, I would say even if this were 9.3, I might say, you know what? It's really going to take 10 years. Because at 9 years, it's not quite there yet. So I will have another video that I'm hoping to make to discuss about that. But this one's easy because I just rounded up to 10 years. But if it says round to the month, what do? Well, I've got 9 years, right? Because that's the first part. But then it's like 0.6, so it's like half a year. So maybe 6 months. How do you figure that out? Let me show you. Take the answer. Oops. Ooh, I'm getting sleepy. Sorry. Take the answer. And then subtract 9. So let me show you. The answer, see, it's still there. Don't let it disappear. I'm going to subtract out the 9. Those are the whole years. This is just the decimal, so you get just the decimal. And here I'm speaking like a person because obviously, you can make the case that every number that's not fractional is actually a decimal, but you know what I mean. The decimal to the right of the decimal point. And then go ahead and multiply by 12. And I get 7.87 months. So that's about 8 months. Does that make sense? So it's 9 years and 0.65 of a year. That's about 8 months. So the final answer would be 9 years, 8 months. Okay. Wow, that was a lot. I realized that was a bunch of math and not all of it entirely fun. And yeah, I ran out of room. I should have gone to another page. I apologize. But we did it. And hopefully you can pause this and rewind. And I will promise you that we're going to go back and cover this subject over and over and over again in chapter 6. So with any luck, by the time we get about halfway through chapter 6, you're going to be like, oh yeah, anytime I need to get an exponent out of the exponent, I'm just going to bring in my logarithm, bring it all down, and life is good. So you guys are awesome. Next up is 5.3, where we will work on yet another application, but kind of a fun application, I think. And then we'll be done with chapter 5. Chapter 5 is, again, very brief. We're not going to cover it as fully as we would if this were just an algebra class, because again, we're just getting those little techniques that are going to help us with chapter 6 and beyond. So congratulations, good luck on the homework. Know that you're awesome, know that I want you to succeed, and I think you're amazing, and woohoo, and math on.